Hello, this is the demonstration project presentation for MAE 535. We are graduate students at North Carolina State University. Our names are Cody, Jan, and John. And Jan will begin by explaining some background information about piezoelectrics.
For the non-piezoelectric material, the overall charge of the positive and the negative ions is in the unique cell, and even with applied deformation, they cancel out and no overall polarization appeared. For the piezoelectric material, when the material is compressed, the distance between the atoms remains the same, which is only possible by expanding the material horizontally, creating an electric dipole. When the material is in a free state, these molecules will be arranged in a certain way, which corresponds to an equilibrium of the matter in which the charge of the molecules cancels itself. When a pressure is applied, however, these molecules change positions and align into a dipole state. In an uncompressed crystal, the positive charges and the negative ones just cancel each other out. The charge distribution is none. When you compress the crystal in certain orientation, you are slightly shifting the average position of the positive charges in one direction and the average of negative ones in the other. This creates some positive charges on one face and the negative ones on the other face.
There's another phenomenon known as the converse piezoelectric effect that also applies to piezoelectric devices. It's essentially the reverse of the piezoelectric effect. With the converse effect, when a voltage is applied, the molecules change position to align with the applied electrical field. This deforms the piezoelectric material. Depending on the material configuration and the current direction, the piezoelectric can either expand or contract, and this is useful for a variety of applications, including the image you can see to the top right of a piezoelectric actuator being used in what is known as a slipstick motor. Taking use of the converse piezoelectric effect allows you to adjust the distance between objects on a nanoscale, making piezoelectrics very useful when it comes to actuation. Both the piezoelectric effect and the converse piezoelectric effect can both be described mathematically as a combination of the material's electrical behavior and Hooke's law. So you can see in these equations, D is the electric flux density, epsilon is the permittivity, and E is the electric field. And Hooke's law, S is the linearized strain, lowercase s is the compliance, and T is stress. These two equations can be rewritten in a form of coupled equations known as the strain charge form. These coupled equations can be written in matrix form as you see below, where the first matrix equation is that of the converse piezoelectric effect, and the second matrix equation is that of the piezoelectric effect. Piezoelectrics are used for a wide variety of applications. Some examples of their applications include microphones, pickups for guitars, so making electric guitars out of acoustic guitars, actuators, such as the one I mentioned on one of the previous slides, high voltage pulses, and is also used in things like ultrasonic transducers for medical imaging equipment and non-destructive testing. For our demonstration, we really would have liked to have used a piezoelectric actuator. However, due to time constraints with shipping times, we were unable to do so. So instead, we elected to create our demonstration around a much more readily available piezoelectric buzzer.
So here are the two components we used for our demo. This is a piezoelectric disc sensor, which showcases the piezoelectric effect. So when you tap on this, it creates a voltage. And then here is a piezoelectric speaker, which showcases the inverse piezoelectric effect. So it receives a voltage and then vibrates and emits a sound. So the other main part of our demo build is an Arduino Uno that we use to process the analog input from the disk sensors. So this is the code that we use, that when you plug one of the disks up to the Arduino, it gives an arbitrary value when you press it from 0 to 1023. And this code just takes that sensor value and converts it to a voltage between 0 and 5 volts. So here is one sensor disk that is hooked up to the Arduino. And if we run the code that I just mentioned, we can see that every time I press it, we get a different voltage reading that it jumps up and down. So here is just a basic schematic of the actual demo build. So you have the Arduino in the middle, and on the left side you have the power source to actually run the Arduino, and that's just hooked up to my computer. And then on the top line you have all the different piezoelectric speakers hooked up to different output pins. And then along the bottom, you have the 5 different piezoelectric disc sensors hooked into the analog input pins. And as you can see that there are different notes next to each of those, which you'll see on the next slide with the code that we actually used, where we adjusted the frequency associated with each disc sensor to play a different note. So this is the actual Arduino code that we use for the piano. And the setup at the top is just initializing the output pins with each of the speakers. In the loop is just an if statement associated with each sensor that if the sensor reads above some certain arbitrary number, it activates the buzz function that we created there at the bottom that outputs to a certain speaker at a certain frequency for a certain amount of time. And the frequencies that we chose there were 5 sharp notes from a piano. So here is the final piezoelectric piano, where you have the 5 disc sensors here at the bottom, the 5 speakers at the top, the Arduino Uno, and then this is just a perf board to hook up all the grounds because the Arduino only has 3 ground pins. So without further ado, here is Old MacDonald on a piezoelectric piano.